Hello and welcome back to MathsBytes and the binary number series. This is video 8 and today we will talk about how to convert decimal numbers to binary numbers using the binary place value table. I will show you many examples again. You will have a chance to practice these conversions, and at the end of the video we will come up with our step-by-step instructions for these conversions. Before we get into converting decimal numbers to binary numbers, I would like you to take a few minutes to draw out the binary place value table again, as we will use it for our calculations. Here is the binary place value table. I hope you got it right, but if for whatever reason something is missing from your table or something is in the wrong place, try to investigate why this mistake occurred. So next time you don't make this same mistake, and don't forget, mistakes are learning opportunities. Next, can you remember what we did when we converted binary numbers to decimal using the place value table? Pause the video here and try to write down the process. Don't just think about it, but actually write it down. We are prone to confirmation bias, and once we hear something, we easily fool ourselves into believing we said the same thing. Writing down things prevents this very common mistake and will help your long-term learning become more effective. Here is one way of writing down the process of converting a binary number to a decimal number using the place value table. Place the binary number to the binary place value table, starting with the rightmost digit in the unit place value and filling in the table with the rest of the binary number from right to left in a kind of backwards way. Then multiply the binary digits with their place values, and finally adding these multiples up to get the decimal equivalent. In the last step, we record the answer using the binary and decimal notation in the bottom right-hand corner of the numbers. For example, to convert 11011 to decimal, we place it to the place value table. Then we write out the sum of 1 times 16 plus 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1, which is the same as 16 plus 8 plus 2 plus 1, or 27. Therefore, 11011 in binary is equal to 27 in decimal. Now, let me draw your attention to this final sum. 16 plus 8 plus 2 plus 1 equals 27. What happens here? Well, our decimal number is written out as a sum of the binary place values. So, if we can figure out what exact binary place value combination a specific decimal number is, then we have converted our decimal number to binary. Let us see this in action and find the binary equivalent of 72. Here is the blank binary place value table to help us. Let us start using up the digits from the right. 1 plus 2 makes 3, plus 4 makes 7, plus 8 makes 15, plus 16 makes 31, plus 32 makes 63. Now we are in trouble, as we only need 9, but the next place value is 64, and if we use it, we will get a number way much more than 72. So we will have to skip some of the place values we already used. But which one? Well, 72 is an even number. Every place value except the unit value is also even. So we should skip the unit value, or we end up with an odd number. You may remember that the sum of even numbers is always even. If not, go on and do a search online to convince yourself of this fact. Anyway, now that we can leave out 1, what else should we leave out to make 72? 32 and 64 makes 96, which is more than 72, so we cannot use both of them. We tried to use everything up to 32 and it didn't work, so let us try using 64 but leave out 32. Now, if we take out 64, then we still need 8 to make 72. How lucky! 8 is one of our place values. So 72 is equal to 64 plus 8. When it comes to binary numbers, we can only use 1 and 0 to express these numbers. 1 means we use a specific place value, and 0 means we don't use a specific place value. For 72, we only need the place values of 64 and 8. Therefore, we will place a 1 into those place values and we need to place zeros into all of the other place values in our table, which will look like this. Let us write down this binary number 01 001 000. Now let me ask you a question. Do we need the very first zero on the left hand side, the leftmost digit? What happens if we leave it out and write 1001 000? Actually, nothing happened. A leftmost zero digit is called a leading zero, and in this specific scenario, this digit does not contribute to anything in our number and can be left out without changing the binary number. Just as I could write 019 instead of 19, it would mean still the same number, but this extra zero on the left looks weird with the decimal numbers. Can you think of an example in everyday life where you see decimal numbers with leading zeros? If so, comment down below. Now, there will be instances when the leading zero cannot be deleted from binary numbers, such as when we will talk about 2's complement notations or introducing the floating point notation. As in those scenarios, the leading zero will have a specific meaning. But let us not get ahead of us. We better make sure we can walk before we try to run. Next question. Do I need the zeros in the other place values in the binary number? Can I also leave out, let's say, the last 3 zeros? Well, the situation with those zeros is slightly different. If we left them out, we would have the binary number 1001, which is definitely not equal to 72. These zeros are the placeholder zeros and are absolutely vital in helping us build the correct decimal number. Remember the examples of 2005 and 25 from video 4? 2005 is very different from 25 in the same way as 1001 is very different from 1001,000. In a sense, you can leave out the leading zero in basic decimal conversions, but cannot leave out the placeholder zeros without changing the value of a number. Now let us wind back a little and try to remember what we did to convert 72 to binary. We used trial and error to come up with the right binary place value combinations to make up 72. When we started with the smallest place values and just added them up one after the other, we ended up in a pickle pretty fast. However, when we started with the higher place values, we got the right combination pretty fast. Was this just luck? Let us try again and see if this would work with another number. Let us convert 97 to binary. Again, here is the blank binary place value table to help us with the place values. Let us start adding the place values from the smallest again and see if it will work this time. 1 plus 2 makes 3, plus 4 makes 7, plus 8 makes 15, plus 16 makes 31, plus 32 makes 63, plus 64 makes 127. We have ended up with a sum that is too much for our 97. Now, we can try to leave out some place values and keep others, but you can probably agree with me that this somewhat haphazard way of finding the decimal equivalent is not too efficient. We need a better plan. So, let us see if we started with the largest place value again would make this process faster. The largest place value in our table is 128, simply because I stopped here when creating the table. However, 128 is bigger than 97, so this place value will not be useful for our conversion. The next place value is 64. This is smaller than our number, so it can contribute to the correct sum. Let us calculate how much more we need if we used up 64. 97 minus 64 is equal to 33. Yay! We are in luck again, as 33 is the sum of 32 and 1. So 97 is equal 64 plus 32 plus 1. So here is the filled binary place value table. Therefore, 97 in decimal is equal to 11,000,001. Again, we left out the leading zero when copying the binary number from the table, as that does not contribute to the value of our binary number, but we kept the place value holder zeros as they are vital for communicating the correct binary values. Okay, now we have seen two examples in which starting the conversion by adding the smallest place values does not work. Let us not waste more time, and for the next conversion, just start straight away by using up the largest possible place values first. Let us convert the decimal 153 to binary. Here is the blank place value table again. 153 is bigger than 128, so we can use up this place value to build up 153. 153 take away 128 is 25. Looking at our place value table, 64 and 32 are too big to build up 25. So the next place value we could use is 16. 25 take away 16 is 9. Now, 9 is equal 8 plus 1. So, 153 is equal to 128 plus 16 plus 8 plus 1. Placing these into the binary place value table, we get. Now let us remind ourselves what the filled table actually means. 153 is equal to 1 times 128 plus 0 times 64 plus 0 times 32 plus 1 times 16 plus 1 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1. This gives us a way to check if we did the conversion correctly. You just have to add up the sum from the place value table again and you will see if you have made a mistake or not. Another way of checking your answer could be to use the shortcut method introduced in the previous video. The advantage of using the shortcut method would be that you are forced to think about the conversion in a slightly different way. So, if you did make a mistake, you are more likely to spot it. In this case, 128, 16, 8 and 1 do add up to 153, so we are good to go. Remember, even if you are allowed to use the calculator, a quick check will go a long way. Let us do 2 more examples before it will be your turn to try these calculations. Let us convert the decimal 215 and 352 to binary. Here is the blank binary place value table again to have our calculations. Let us start with 215. The biggest place value from the table that is still smaller than 215 is 128. So let us take it from 215 to see what is left over. 215 take away 128 equals 84. The next place value is 64. This is smaller than our remainder of 84, so we can use it. 84 minus 64 is 20. Now, 32 is too much for 20, but 16 isn't. And the remainder after taking 16 from 20 is 4. Therefore, 215 is equal to 128 plus 64 plus 16 plus 4. Let us place this into our place value table. We have used up 128, so let us place a 1 on that 128. Next, place value we used is 64, so 1 goes into that column too. Then we need to place a 1 into the 16 columns and into the 4 column. All the other columns will have 0 in them. Finally, we can write down that 215 in decimal is equal to 110101000 in binary. Let us convert 352 to binary. Let us keep taking away all the place values that are smaller than our number and record the remainders. 352 take away 128 is 224. 224 take away 64 is 160. 160 take away 32 is 128. 128 take away 16 is 112. 112 take away 8 is 104. 104 take away 4 is 100. 100 take away 8 is 98. 98 take away 1 is 97. What is wrong here? We used up all the place values, but there is still 97 that we need to make up to finish the conversion. Now, we cannot use any place values more than once, as in binary, we only have the digit 1 and 0. So we either use the place value once or we don't use it at all. Where could we have gone wrong? Actually, if we look at the remainders at each step in the calculations, they are way bigger than the next available place value. This indicates that we started with a place value that is too small for our number. Our place value table has the highest place value of 128, as I just stopped at this value. But this is too small for 352. Let us add another column with the next place value up to get. And let us start again. 352 take away 256 is 96. Now this is better. The remainder is in the same magnitude, size, as the available place values and not much bigger than in the previous try. Let us carry on. 96 take away 64 equals 32. And bingo, we are done. So 352 is equal to 256 plus 64 plus 32. Now, this is much better. We can now fill in our place value table by writing a 1 into the place value columns of 256, 64 and 32 and placing a 0 everywhere else. This gives us the binary equivalent of 352 as 1, 0, 1, 1, 0, 0, 0, 0, 0. It is worth mentioning again that if in your calculations the remainders seem too big for the available place values, you probably started with a place value too small. Go back and revise your binary place value table and extend it if necessary. Now, I would like you to spend a few minutes and try to summarize what we do when we convert a decimal number to a binary number using the place value table. Pause the video here and have a go at this task. Here is one way to write down how the decimal to binary conversion works. Find the largest place value that is still smaller than the decimal number and subtract this from the decimal number. Look at the remainder and find the largest place value that is still smaller than the remainder and subtract this from the remainder. Keep repeating until there is no more remainder. Write down the decimal number as a sum of the binary place values identified in the repeated subtraction. Place a 1 into the binary place value table columns that were used in the sum and place a 0 everywhere else. Now copy down the binary number and check if your calculation is correct. I am sure your description is different. After all, we all have our own style of expression. Look at your description and see if you have covered the main steps, such as the repeated subtraction and the placing the right digit into the place value tables and the very important step of checking your answer. The step of writing down the decimal number as a sum of the place values is not strictly necessary for the solution, but it is a nice aid to help you along the process and makes the next step of filling out the place value table easier. Right, now that we are all on the same page, and hopefully you are pretty clear on how to convert decimal numbers to binary using the binary place value table, here are a few practice questions you can try. If you are unsure what to do, just use the method description on your paper or the one I gave you. After all, you are still learning this process, so don't expect yourself to be able to do it all at once without any help. That is very rare. It certainly wasn't true for me when I first learned about these calculations. Here are the answers. I hope you got the answers right, but as I keep saying, mistakes are learning opportunities. If you did make a mistake, don't get discouraged. Instead, try to see the mistake with curiosity and try to figure out what a particular mistake is trying to teach you that you may have missed earlier. In the last part of this video, I would like us to come up with a step-by-step instruction for converting decimal numbers to binary numbers using the place value table approach. We have already tried it to some extent before the practice questions, but this time I would like us to be more precise and put it into a formal description that is clear and concise. Here is my version. I hope your instructions are similar. You don't need to have the same number of steps, just make sure the process is clear and captures the same flow. Then write either your own method or mine to your flashcards and make sure you test yourself regularly to ensure you remember the process. If you want to make the learning process extra effective, I challenge you to shorten down the above instructions just to a few key words that triggers your memory of what needs to be done in each step. This way, your retrieval practice with the flashcards will be super effective. Also, don't forget that seeing 5 examples and trying 3 calculations will only help your understanding of the process. For you to truly master these calculations and get the best grades you want, you need to practice more questions and do spaced practice. Basically, don't cram. Don't do loads and loads of questions of the same type in a short amount of time, but rather do a few different types of questions day after day. This way, you will see and understand the similarities and differences of the different types of questions, and you will become better at making the judgment of what type of approach to use for a set type of question by the time of the exam. Even weeks after you covered this topic, make a conscious effort to try these questions. This is a proven way to become an expert at any skills. Let us now recap what we covered in this video. Also, don't forget to rewatch any of the previous videos in the series if you feel you could benefit from revisiting some of the earlier concepts. So, in this video, we talked about how to convert decimal numbers to binary using the place value table. We discovered that every decimal number can be written as the sum of a few specific binary place values, and if we found a way to find this combination, we could do the conversion. We tried to add all the place values together from the smallest place value, but that didn't work. We then settled for trying with the largest place values that was still smaller than our decimal number, and we repeatedly subtracted place values from the original decimal number and the remainders until we were left with no more remainders. Then we have written out the decimal number as a sum of these binary place values, and next filled in the binary place value table, placing a 1 into the columns that were part of the sum and a 0 everywhere else. Finally, we have written down the binary number from the table. While we did some practice questions, we also discussed what leading and placeholder zeros are, and the fact that leading zeros can be left out in ordinary numbers, both decimal and binary, without changing the value of the number. This cannot be said about the placeholder zeros. We need the placeholder zeros to make sure we have the right binary or decimal numbers. You also had a chance to practice some conversions, and I hope you did take this opportunity and will do more practice, but of course it is up to you. After all, you are in control of what you do and don't do. In the final part of this video, we have formalized the process with a 6-step instruction, and I also gave you some advice on trying to make your learning more effective by using flashcards for retrieval practice, and I also talked about spaced practice. I truly believe if you apply these simple learning hacks, your learning will take to the next level. I hope you found this video useful and you learned something new. In the next video, we will revisit the decimal to binary conversion, and I will show you another method, which I believe is a faster way of converting the decimal numbers to binary, but again, without the work we had done today, that shorter conversion method might not be clear enough. I hope to see you in the next video, and until then, keep learning, one byte at a time.